Hello, good morning everybody. I am VR Seshagiri Rao, Associate Professor in the Department of Electronics and Communication Engineering, IARE. I welcome you all to this series of lectures on electronic device and circuits subject. Today I am going to discuss about the half-wave rectifier. So what is a rectifier? A circuit that converts AC voltage of main supply into DC voltage using one or more diodes is called as the rectifier. So AC regularly reverses the direction. So that means it changes from positive to negative and then from negative to positive, while the DC flows only in one direction. So direct current is necessary for the operation of many devices such as laptop computers, televisions and uh, PCs and certain power tools. There are three types of rectifiers: half-wave rectifier, full-wave rectifier and the bridge rectifier. Depending upon the number of diodes that are being used and depending upon the scheme of rectification. So there are three types of rectifiers: half-wave rectifier, full-wave rectifier and the bridge rectifier. So in half-wave rectification, either the positive or negative half of the input AC signal is passed. Only either positive half is passed or negative half is passed. So only when one half of the input waveform reaches output, we get the pulsating DC. Typically, the half-wave rectifier circuit consists of three main components: diode, transformer and the load. So this is the circuit of the half-wave rectifier, and this is the AC source, and this is the transformer section, and here we have one diode, and this is the load. So transformer, normally we use the step-down transformer, wherein 230 volts AC is applied and it is a step down to lower voltages, and the lower voltage is rectified using this diode. So there are three sections. One is the transformer section, and another is the rectifying section, and last one is the load section. So there are three sections in the half-wave rectifier. So in half-wave rectification, as we discussed just now, either the positive or negative half of the AC wave is passed, while the other half is blocked. Now let us see the working of half-wave rectifier. So the input which is applied from the secondary coil of the transformer is a sine wave. So there are two cycles, the positive half cycle and the negative half cycle. So the input voltage is V is equal to Vm sine omega t, where omega t lies between 0 and 2 pi. So this is pi and this is 2 pi. So from 0 to pi it is a positive half cycle, and from pi to 2 pi it is a negative half cycle. Now let us see the working of the half-wave rectifier in this configuration. Okay, so here when there is a positive swing, what happens? The diode is forward biased, and when the diode is forward biased, it liberally allows the flow of current, and we get current flowing in this way through the load and then back to the transformer. Okay, so we get when the current passes in this direction, we get a positive half cycle, and the diode can be assumed as a switch. An ideal diode behaves like a mechanical switch. So when the diode is forward biased, we know that it acts like a closed switch, and when the diode is reverse biased, it acts as a open switch. So the current direction here is node A to diode, then load R, then node B. So in this way, the current flows. So when the current flows to the resistor, we get output voltage So when for the positive half cycle, we get the positive half voltage. Now during the negative half cycle, when the voltage is negative, and this is a diode, the diode is replaced with an open circuit. When you apply negative voltage to the anode and positive voltage to the cathode, the diode is reverse biased and it does not allow passage of current. So it acts like a open switch. So that's why this is represented as into mark. So the diode is reverse biased and it acts as open circuit. So when it is open circuit, there is no flow of current and the voltage across the load resistor is zero. So we get, for the negative half cycle, we get the output voltage as zero in this way. So a high AC voltage, when it is applied to the primary side of the step down transformer, the obtained secondary low voltage is applied to the diode. So the diode is forward biased during the positive half cycle of the AC voltage and it is reverse biased during the negative half cycle. So this is represented in more elaborately here. So here this is the input voltage. If you take this as the diode and this is the load and this is the secondary coil of the transformer. Okay. So here the input voltage, this is Vn and it varies in both directions. So for the positive half cycle, just now as we discussed, the diode conducts and we get the positive output. And when the Vn is negative, the diode acts like a open switch and the output voltage across the load is zero because the current through the diode is zero. So we get the zero output. And again, when the diode voltage goes positive, we get a positive output. When the diode voltage goes negative, input voltage goes negative, we get the negative. And again, here we get the positive. And like that, we get a pulsating DC, and this is the final waveform. Now, let us calculate the following parameters for the half-wave rectifier. What is the DC output current? Let us calculate. Then what is the DC output voltage? RMS current, RMS voltage. What is the ripple factor? Rectifier efficiency, output frequency, and PIV, the peak inverse voltage, the peak factor, form factor, and transformer utilization factor. Let us calculate all these parameters for the half-wave rectifier. Okay. Now, what is the average value of current and average value of voltage? Let us see. See, what is the average value of, when we apply this is the load RL and this is the diode. Okay. So when we apply a input sine wave Vn, during the positive half cycle, we get a sinusoidal output current and a sinusoidal output voltage. So what is the peak value of current? What we get? The peak value of current Im, what we are going to get, Im is equal to, we have to take the peak value of the input voltage. Now let us assume that Vn is equal to Vm sine omega t. Then what is the peak value of current? Im is equal to Vm divided by, we have to take the coil resistance. Of course, it is very less. So Rs plus we have to take the diode forward resistance, which is nothing but Rf plus RL. So this is a peak value of current what we are going to get when we apply the input sinusoidal voltage. And Rs is the transformer series resistance, and Rf is the diode forward resistance, and RL is the load resistance. So what is the average value of DC current? The average value of DC current is IL. IL is equal to Im sine omega t. So this is during the positive half cycle. So this is for the value when omega t is 0 to pi. So when omega t assumes values between 0 to pi, IL is equal to Im sine omega t. And IL is equal to 0 otherwise. So that means for omega t between pi to 2 pi. So when omega t is between 0 to 2 pi, IL is equal to 0. Now under these conditions, let us find out what is the average DC current. So IDC is equal to, we have to take what is the total angle 1 by 2 pi, and we have to take 0 to pi Im sine omega t and d omega t plus pi to 2 pi 0 omega t. So this is equal to 1 by 2 pi and Im. What is sine omega t? That is the integral minus cos omega t. And we have to evaluate its value in the value 0 to pi. So this is going to give us the value as Im by pi. So Im by pi is the average of DC load current. Yeah. Now what is the average DC voltage? What is the voltage? Voltage is nothing but current multiplied by the resistance. So what is the resistance? The resistance is RL. So we have to take the value of RL, then calculate the average DC voltage. So the average DC voltage is also called as VDC or EDC. So that is nothing but IDC multiplied by RL. What is IDC? Just now we have calculated, and it is Im by pi. So Im by pi into RL. So that is the average value of the DC voltage. What is Im? Im is nothing but, we have calculated the Im. Im is Vm by Rs plus Rf plus RL. So Vm by pi into Rs plus Rf plus RL into RL. So this is the average DC voltage. Now let us find out the root mean square value of the current and voltage. So RMS value of current. So as the name indicates, it is, we have to square the load current and we have to take a mean of it. Then we have to find out the root of it. That is going to give us RMS value of current. So IRMS is equal to, and we know that the load current or the load voltage is available only for half of the input cycle. So it is available only for 0 to pi. So IRMS is equal to, we have to take 1 by 2 pi and 0 to pi, and we have to take the square of the value, that is I is equal to Im square sine square omega t d omega t. So this is a mean square value and we have to take the root of it. So the root of it we can get by taking the half, by taking the root. So this is the value what we have to compute. So we have to do the integration and then we have to find out the corresponding value. So here we get the value like this. So this is equal to Im. Because this Im square, let's take it up the root. So we get it as Im and square root of 1 by 2 pi. Let us take sine square omega t. It is nothing but cos 2 omega t divided by 2. So we have to, for sine square omega t, we replace it by 1 minus cos 2 omega t divided by 2. So you replace it and then do the integration, then we get, so omega t by 2 minus sine cos 2 omega t, sorry, sine 2 omega t divided by 4, and we have to evaluate it, the angle between 0 to pi. So this will give us the RMS value as Im by pi. You simplify, you get the root mean square value as Im by pi. And what is the root mean square value of voltage? So that is equal to VRMS. So that is equal to Im by pi into RL, because the output voltage appears across a load. So Im by pi into RL, so that we give us the RMS value of current. Now let us find out the DC power output. So how do you calculate the DC power output? Power is nothing but current multiplied with the voltage. So we multiply the IDC with EDC or VDC, you get the DC power output. So DC power output is given like this. The DC power output we get PDC is equal to EDC multiplied by IDC. And what is EDC? EDC we have calculated just now, and it is Im by pi into RL. That is nothing but the EDC. And what is IDC? IDC is Im by pi. So what is the value of the DC power output? It is nothing but Im square RL divided by pi square. So this is the value of the DC power output which is coming from the rectifier after rectification. And what is the AC power input? Let us see. And AC power input we get by calculating the RMS value of the voltage and current. So AC power output we get like this. AC power input we get PAC is equal to, we have to take the RMS value of current, IRMS square, and then multiply it by the resistances which are involved in the circuit. What are the resistances that are involved in the circuit? Series transformers secondary resistance, which is RS, diode forward resistance, which is RF, and the load resistance. So this is multiplied by RS plus RF plus RL. So this is PAC. Okay. Now what is the rectifier efficiency? See, the rectifier efficiency is defined as the DC power output divided by the AC power input. See, certain amount of power is given to the circuit, and how much total power is coming out, that is nothing but the rectifier efficiency. So rectifier efficiency is defined as the output power divided by the input power. That is nothing but the rectifier efficiency. So rectifier efficiency we are going to get by taking the DC power output and the AC power input. And what is the DC power output? It is nothing but Im square by pi square into RL. And what is the AC power input? AC power input is IRMS square. So IRMS into RS plus RF plus RL. So this is the, and what is IRMS? IRMS we have calculated, and IRMS is nothing but Im by pi. This is the IRMS, Im by pi. So let us substitute this value here. So we get here Im square by pi square. Sorry, Im square by pi square into RL divided by, and IRMS square is nothing but Im by 2. So Im square by 4 into RS plus RF plus RL. So we get this as 4 by pi square into RL by RS plus RF plus RL. So neglecting the diode forward resistance and the transformer secondary winding resistance, we get the rectifier efficiency as 4 by pi square. 4 by pi square. So what is 4 by pi square? For pi is around 3. So 4 by 9. So that will give us the rectifier efficiency nearly as, so eta, we call eta as the rectifier efficiency. So eta we will get eta as 4 by pi square and into 100. So this is 0.406 into 100. So we get 40.6%. So that is the rectifier efficiency. So that means, suppose if I am giving 100 watts input power, output power I am getting only as 40.6. So what is happening to the remaining power? It is going to appear across the diode and the transformer when the diode is not conducting. So when the diode does not conduct, what happens? The power is dissipated by the diode and the transformer secondary winding. So only 40.6% of input power is delivered to the load. So that is the efficiency of the half-wave rectifier. So you can understand that the half-wave rectifier efficiency is poor. It works with less than 50% efficiency. The next parameter what we have to discuss is the ripple factor and voltage regulations and all that. So let us see now the ripple factor. So ripple factor, I'm going to define ripple factor like this. The ripple factor is defined as gamma, so that is equal to RF. So RF is the ripple factor and that is equal to IAC by IDC. So ripple factor, it indicates the amount of AC variation in the output. See, ideally speaking, there should be no AC variation in the output for a rectifier. So the ripple factor should be ideally 0. So the smaller the value of ripple, the better is the rectification. So ripple factor, it indicates the quality of DC output. So ripple factor is equal to IAC by IDC. So what is IRMS? So you know that IRMS is equal to IAC square plus IDC square. This is the IRMS. So from this, IAC square is equal to IRMS square minus IDC square. So IAC is equal to IRMS square minus IDC square root. So that is a IAC. So now the ripple factor RF, it is IAC by IDC. So IRMS square minus IDC square root divided by IDC. So this is equal to IRMS square by IDC square minus 1. So that is the ripple factor. So what is IRMS? We have just now calculated IRMS as IM by 2. IM by 2 is the, this is IM by 2. So this is IM by 2. That means IM square by 4. And what is IDC? IDC is IM by pi. So into pi square divided by IM square minus 1. So this is equal to pi square divided by 4 minus 1. So this is the ripple factor. So pi, it is 3. So 9 by 4 minus 1. So this will give us the value as 1.21. So this is a ripple factor. So the ripple factor is very high for half-wave rectifier. Ideally, the ripple factor should be 0. Next, let us move on to the peak inverse voltage. So the peak inverse voltage is the maximum voltage which appears across the diode during operation. So there is a peak inverse voltage. And this is a very important parameter. When you choose any diode in the half rectifier, we have to take the PIV rating of the diode. So what is the maximum voltage the diode can withstand? That parameter has to be kept in mind for choosing the diode in the half-wave rectifier application. So the maximum voltage which appears across the diode during operation of the circuit is called as the peak inverse voltage. This is a very important parameter. So for half-wave rectifier, what is the peak inverse voltage? So this is a half-wave rectifier, the load resistor RL, and the transformer secondary coil, and the current is, the voltage is Vm sine omega t. So when voltage is positive, yes, the diode is forward biased and practically zero voltage appears across the diode. But when the voltage becomes negative, Vm, the diode is reverse biased and the total voltage appears across this diode. So what is the maximum voltage? You get minus Vm. So the peak inverse voltage is Vm. The peak inverse voltage is Vm. Suppose if the maximum amplitude of the input wave is 10 volts, then the peak inverse voltage is 10 volts. So we have to choose the diode with a PIV rating of 10 volts. So that means the diode should withstand a maximum voltage of 10 volts. Suppose if you choose a diode which is low rated, the diode will be damaged. The diode is going to be damaged during operation of the circuit. So peak inverse voltage is a very important parameter which has to be kept in mind for choosing the diode for half-wave rectifier operation or half-wave rectifier application. Next, the parameter is transformer utilization factor. So transformer utilization factor is the DC power delivered to the load to the AC power rating of the transformer. That is a transformer utilization factor, TUF. So TUF, it is defined as the DC power output delivered to the load divided by the AC power rating of the transformer. So we get here PDC. TUF is nothing but PDC divided by the AC power rating of the transformer. So here we take the RMS value of the voltage and the current. So ERMS and multiplying it by the IRMS we take. That is the AC power rating of the transformer. So TUF is nothing but DC power delivered to the load to the AC power rating of the transformer. So what is the DC power delivered to the load? IDC square multiplied by RL. So that is, and what is the AC power rating of the transformer? VRMS multiplied by IRMS. So what is VRMS? VRMS is nothing but IM RL divided by root 2. That is a ERMS. The input voltage varies in both directions. And what is IRMS? IM by root 2. So once we simplify this, we get as 2 root 2. So, for IRMS, of course, it is root 2. Sorry, 2. So this we get as 2 root 2 divided by pi square. So this we get this as 0.287. So this is the transformer utilization factor. So these are all the parameters what we have discussed about the half-wave rectifier. We have derived the values for the DC output current, DC output voltage, RMS current, RMS voltage, input factor, rectifier efficiency, and so on. So the average or DC current value is nothing but the average average power delivered to the load. So IDC is equal to IM by pi, that is equal to VM by pi into RF into RL. And average or DC voltage, VDC, is equal to IDC multiplied by the load resistance. And as VDC is equal to VM by pi, so this is the average DC voltage. And RMS current value is IM by 2. And that is equal to VM by 2 into RF plus RL, where RF is the diode forward resistance and RL is the load resistance. And RMS voltage is VM by 2, assuming that RF is negligible compared to the load resistance. And rectifier efficiency, it is the ratio of DC output power to the AC input power. So it signifies how efficiently the rectifier circuit converts the AC power to the DC circuit. So this is output power divided by the input power multiplied by 100. So we have seen that it is less than 50%. So PDC by PAC into 100. So PDC is equal to IDC square into RL divided. So that is equal to IM square by pi square into RL. So PAC is equal to PD plus PL. So we get this as IM square by 4 into RF plus RL. So after simplification, we get the rectifier efficiency less than 50%. So it is 40.6%. So suppose if the input power is 100, only 40.6 watts is delivered to the load. And ripple factor is, it indicates the amount of ripple present in output voltage or output current, and that is equal to 1.21, and ideally this should be 0. So these are all the various parameters of half-wave rectifier, and the half-wave rectifier, the disadvantage is the average value of load current is less, the average voltage is less, and it has high ripple value, and the efficiency of transformer and transformer utilization factors are less, and the design is modified in full wave rectifier by using 2 diodes. So that we will see in the next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.